In the previous lecture, we discussed the simple stresses and strains. In the present lecture, we will discuss the elastic limit and the Hooke's law. First, we will discuss the elastic limit. We know that elastic material undergoes a deformation on the application of a loading such that the deformation disappears on the removal of the loading. For every material, the property of regaining its previous shape and size is exhibited on the removal of the loading when the intensity of stress is within a certain limit called as the elastic limit. So every material possesses the elasticity, but loading should be within a certain limit. That limit we are calling as the elastic limit. If after exceeding the elastic limit, the loading is removed, the member will not regain its original shape and a residual strain or permanent set remain. Which means, if the loading is less than the elastic limit, material possesses the elasticity property. If loading exceeds this elastic limit, material goes to the permanent deformation. Next, we will discuss the Hooke's law. Hooke's law stated that when a material is loaded such that the intensity of stress is within a certain limit, the ratio of the intensity of stress to the corresponding strain is a constant, which is a characteristics of that material. So Hooke's law stated that stress and strain have directly proportional up to the certain limit of the loading, that is we are calling as the proportionality limit. So if we are loading the material within the proportionality limit, stress is directly proportional to the strain. Then the ratio of intensity of stress to strain is the constant. So ratio of the intensity of stress and strain equal to the constant, that is the sigma is the intensity of stress. So epsilon is the strain. So sigma by epsilon equal to the constant. This ratio is called as the Young's modulus or modulus of elasticity, and it is denoted by the capital E. So sigma by epsilon equal to the capital E. So stress by strain equal to the Young's modulus or modulus of elasticity. So units of the Young's modulus is the same units of the stress, because E equal to the sigma by epsilon. So but strain we don't have the no units. Then so Young's modulus having the same units of the stress, that is the Newton per mm square. And we know that when the sigma equal to the P by A. So resistance force or applied force divided by the cross sectional area, and strain equal to the deformation per the unit length, that is the delta by L. So equal to the E. So from this equation we can directly write down the deformation value, that is delta equal to PL by AE. So this is the very important formula. So most of the time we will use this formula to solve the problems. So keep remember this formula. In the case of shear loading also, the ratio of the shear stress to the corresponding shear strain is found to be a constant when the shear deformation is within a certain limit. So mathematically I have to say that one. So tau by phi equal to the constant, and this ratio is called as the shear modulus or modulus of rigidity, and it is denoted by the, sometimes we will use C or capital N or the capital G. So mathematically I have to say that one the tau by phi equal to the capital G. So please remember this formula also. Next we will discuss the problems on simple stresses and strain. So let's see the first problem. An elastic rod 25 mm in diameter, 200 mm long, extends by 0.25 mm under a tensile load of 40 kN. Find the intensity of stress and the strain and elastic modulus of the material of the rod. So first we have to write down the given data. So here it is given the diameter, rod diameter. So let's consider diameter of the rod is capital D, that is the 25 mm, and it is given the 200 mm long. So length of the rod is capital L, let's consider, that is the 200 mm, and extend by 0.25 mm, that is the deformation delta equal to the 0.25 mm, and given that one the under a tensile load. So load is given 40 kilonewtons, that to tensile load. So tension, let's consider capital P equal to the 40 kilonewtons, which is equal to the 40 into 10 to the power 3 newtons. So then we have to determine the intensity of stress, strain and the elastic modulus. So we know that one. So intensity of stress sigma equal to the load divided by the cross sectional area. So here load is given, capital P is given 40 kilonewtons. So A is the cross sectional area, but here it is not given directly, but here given the diameter of the rod. Then first we have to determine the area of the section. Let's consider capital A equal to pi by 4 d square. So pi by 4, capital D is given the diameter of the rod 25. Then substitute, we will get the area of the section is 490.87 mm square. So next we have to look for the intensity of stress sigma equal to P by A. We know that one P value 40 into 10 cubed, and A value also we know 490.87. Then substitute, we will get the sigma value 81.49 Newton per mm square. So next we have to look for the next one, strain. So we know strain equal to deformation per unit length. So deformation delta. So length is given L. So delta value is the 0.25 and L value is the 200. Substitute, we will get the 0.00125. So strain have the no units. So next one is the elastic modulus, capital E. We know that one the ratio of the stress to the strain. So sigma by epsilon, which is equal to the sigma value is 81.49, epsilon value is the 0.00125. Then elastic modulus E value is the 61,192 Newton per mm square. So next we have to see the another problem. Find the maximum and minimum stresses produced in the stepped bar shown in the figure due to axially applied compressive load of 12 kilonewtons. So here it is given the stepped bar is given, and one is having the diameter 12 mm, another one is the 25 mm diameter. So upper part is the 12 mm in diameter and lower part is the 25 mm in diameter, and compressive load is applying, the load value is the 12 kilonewtons. Question is asking that one the maximum and minimum stresses produced. Okay, let's see the first write down the given data. So first we have to determine the area of the upper part. So upper part diameter is the 12, then area will become the pi by 4 12 square. So area of the upper part is the 113.09 mm square. Similarly we calculate the area of the lower part, which is equal to the pi by 4 25 square. So which is equal to the 490.87 mm square. So next we have to determine the maximum and minimum stresses. So maximum stresses will be developed which having the minimum cross sectional area. So we know that one the stress equal to load divided by cross sectional area. So where we will get the maximum value mean which having the minimum area. So maximum stresses it will be generated for the upper part, that is the sigma max equal to P by A1. Let's consider the upper part area is the A1. Then we know the P value, compressive load 12 into 10 cube. Sorry, here it is the 10 cube, not 103. So 12 into 10 cube divided by A1 value is the 113.09. Substitute, we will get the maximum stress is the 106.1 Newton per mm square. Next we have to see the minimum stress in the lower part. For that one, P divided by A2. Let's consider A2 is the area of the lower part. We know the P value 12 into 10 cube. So this is also 10 cube. Divided by A2 value is the 490.87. Substitute, we will get the minimum stress value is 24.45 Newton per mm square. Next we look for the another problem. A cast iron column has an external diameter of 300 mm and 20 mm thickness. Find the safe compressive load on the column with a factor of safety of 5 if the crushing strength of material is 550 Newton per mm square. So here it is given the cast iron column which having the external diameter 300 and thickness is the 20 mm. So it is the one of the hollow cylindrical type of the column and the external diameter is the 300, thickness is the 20. Then internal diameter will become the 300 minus 2 into thickness, which is equal to the 260. So external diameter is the 300 and internal diameter is the 260 mm. So let's see the solution. So first we have to determine the area of the part. We know the area of the hollow cylinder, pi by 4 into d1 square minus d2 square. d1 is the outer diameter, d2 is the inner diameter. So area will become the pi by 4 into 300 square minus 260 square, which is equal to the 17,592.78 mm square. So next, safe stress in compression, which is equal to the ultimate strength divided by the factor of safety. So maximum strength, here it is given the crushing strength of material is given the 550. Then safe stress in compression will become the 550 divided by factor of safety is the 5. Then safe stress in compression equal to the 110 Newton per mm square. So then we have to determine the safe compressive load we have to determine. So we know the safe stress we know and also area we know. Then safe compressive load will become the safe stress in compression into cross sectional area, which is the safe stress is 110 and cross sectional area is the 17,592.78. Then safe compressive load will become the 1935.2058 kilonewtons. So this is the solution and thank you.